3753 total waviness of numbers in range 2. The three pillars of the solution 1. The branch multiplier effect. Waviness. Instead of just adding 1 every time we spot a peak or valley, the DFS returns two things: the number of valid ways a suffix can finish, and the total waviness gathered in that suffix. If we find a peak at our current position, we multiply it by the ways the rest of the number can be completed. This correctly propagates the peak's value across all possible combinations that follow it. 2. Smart leading zero handling. isLZ. Because we are evaluating numbers up to 15 digits long, the number 4848 is technically padded with 11 zeros in our DFS, e.g. 000000000004848. Tracking an isLeadingZero state ensures we completely ignore these phantom zeros, preventing the algorithm from falsely counting them as peaks or valleys until the real number begins. 3. Maximum cache reuse, decoupling tight. By intentionally not memoizing states where tight is true, our cache DP table becomes entirely independent of the specific numbers, num1 or num2, we are evaluating. The cache purely remembers, if I have x digits left, and my previous digits were y and z, what is the total waviness? Because of this, solve num2 and solve num1 to 1 get to pull from the exact same memory pool, doing half the work. The optimized solution, we need our DFS to return two things at once: number valid ways, total waviness. We also need to add an isLeadingZero state so we know exactly when the real number begins. Why this runs incredibly fast? By returning ways and waviness together, we avoid needing separate DP loops. By decoupling tight from the memoization array and only caching the suffix states, remlin, we effectively execute solve num2 and solve num1 to 1 using the exact same cache pool without needing to reset it, drastically reducing overhead. Because the dimension footprint maxes out at 18*11*11*2, it practically runs in 01 time after the first few prefix branches.